All right, so thanks everyone for showing up. As you probably already know, this is the 4-day lab course we've put together to run through everything from basic Python automation up through Ansible, up to AVD. We started doing this last year, just before we started officially supporting the AVD as a TAC product. So the goal of this really is to take you from a foundation where we expect you've got basic Python knowledge, walk you through how to use APIs, how to interact with other devices, and we'll culminate with where you'll be deploying a modest AVD topology and managing this through AVD. We'll get into more of this as we go on. There is different layer stacking. The important thing to note is that what we're going to be doing is building on each of the previous days. So if you miss a day, I will have a recording so you can catch up, but it will make it a little harder in some cases. So let's go and look through what we're doing in terms of our agenda for the week. Today, we're starting off with basics of talking about automation at a conceptual building block level, how we use it, how we structure that, and some background explanation on APIs, Jinja, and Git. These will be foundational to what you're doing in the rest of the week. We'll also have some labs for you to make sure you can get acquainted with ATD. You'll be doing some basics of eAPI automation using Jinja and Python. Day 2, we will be going into Ansible itself. We'll be discussing what a collection looks like, how they work in general, and doing some labs with low-level collections. By day 3, we're going into AVD proper. AVD builds on top of Ansible as a layer. We'll be talking about the concept of stacking different layers of orchestration, the concepts AVD has around data structures, design pipeline stages, things of that sort. And then we have an AVD lab. Day 4 is typically marked for overflow. The labs from day 3 does take some time and are usually additional questions. Based on time left, we might also run through some various troubleshooting exercises on concepts like vaulted tokens and things of that sort in Ansible playbooks and inventory. So when we look through the agenda for today, like I mentioned, we're looking through automation, API terminology, and building blocks. You're familiar with various concepts of those and how we use them in our products. And then we'll go into some lab work. So why do we care about automation? It's talked about a lot with networks, but it can be hard to understand at first if you aren't familiar with what it brings as to why we keep using it and why customers care about it so much, even if they aren't doing it themselves. When it comes to networks, uniform network design and deployments save a lot of problems. You guys have probably faced a number of issues where customers done something weird on just one switch and it causes some sort of loop, causes an outage, or just something that wouldn't happen in the network. So by bringing automation, we can ensure that we have uniform deployments, they're cheaper than humans, and it's a lot faster to deploy. These are all things that products like CloudVision bring to the table for customers. This is why we're always looking at automation. Beyond just networks, it can also impact your personal workflow a lot. We use automation for things like doing reporting internally. We have automatic APIs to do things like talk to bug systems and such, to figure out how often we're hitting issues, or figure out when we need to make changes. A large part of our test suite we do here is done automatically, and that's for cost reasons and to ensure we can do thousands of tests every time we build a release. When we look at what happens with automation obstacles, you're going to see a bunch of these from customers typically. A lot of the time, there's statements like they don't have sophistication to do that, there's just enough time, things of that sort. And while these are all valid, we usually have to recognize that there's an upfront cost in time and people to automation, but for a sufficiently scaled project, it does pay off in the end. You're going to see some of that today as we're giving you a larger topology that would, by hand, take you some time to deploy in a CLI, and you're going to see just how much faster it is to iterate and make changes on that as you get into it with automation. So, like I mentioned, there's a number of things we can automate. Looking at the network level, these are some of the categories we often go through and target for that automation. But really, of course, anything can be automated if it has an interface to communicate with it. It doesn't have to be an API. APIs make things simpler, but you can, for example, automate UIs in things like headless browser testing. really what it comes down to is the sky's the limit when you talk about automation. You just have to have sufficient imagination, creativity to figure out how you want to achieve that and then drive towards that goal. When it comes to talking about the culture of automation, we're typically focused on how we can achieve the highest scale and reuse. Because these tools and this kind of automation has an upfront cost in terms of time and people working on it, the more it can be used, the better the return on investment is. So this is why you see so much focus on internally when we're building tools or when SEs or AS is building playbooks and process for customers to do this kind of automation, it's shared because that dramatically increases how helpful and the impact of that automation. Not to mention, when it's shared like that, we can iterate on process among multiple engineers and find issues that are missed by other people and make it overall better. Like this here as well, we're also looking at consistency. We want to make sure that when we have automation, we can account for problems within the workflow itself without users having to be involved. And we want to ensure the outcome stays the same. These are key goals of Ansible as well. When we get into on day 2, you'll see more of how they achieve that within the actual code logic. And finally, this is just the basic guidance we usually give people who are starting out and our customers as well when it comes to dipping your feet into automation. We usually start with the low-hanging fruit. We figure out the easy things that have well-built automation as far as APIs, connection points, things of that sort, and we start there. Once we have that easy automation done, our fastest ROI, we start dipping into the harder stuff. Things that don't have good APIs, things that have complex object graphs, things of that sort. So that by the time we get to those, we already have the culture and the muscles in place to look at how to do that, make it repeatable, and make it work. So let's talk now about how this ties together into what we call the automation pipeline for a network. Typically, when you're looking at how you're going to drive automation to a network fabric, meaning beyond just a single switch in the network, you have to look at a few different stages of the process. You're always going to start with your data from upstream data source, which is going to be something like NetBlocks, your Nautobot, things of that sort, the IPAMs of the world, or user input. And this can also include things like CSV dumps in some cases, Excel spreadsheets, G-Sheet APIs. These all feed into usually a central logic hub, which is your orchestration engine. And what this does is this loads in logic about how you want to build the actual network fabric. It takes that data and applies it to create your actual changes and drive to your desired state. And then finally, you apply that to fabric. This is fairly abstract, so let's make it more concrete. I'll skip through this, we'll go back to this in a second. When we talk about tooling, without a unified solution, you end up with something like this, where different tools own different parts of your pipeline. Like this shows here, you can start with NetBox and other tools that feeds through Python and Jinja in place, and you get down to REST APIs. The reason we use tools like Ansible and AVD is we can abstract all these different parts of that pipeline into what looks like the end user operator, like a single workflow. By using Ansible playbooks and by using that high level orchestration, we can compose these in a repeatable manner. So it's not just that we have a script here that's repeatable, the entire pipeline becomes repeatable. And I'll back up here to just run through these real quick. I'll provide these slides there as well if you want to look through them. But like we described, we basically start with just pulling that input. We do our validation. We do our mapping, our merging. And then we start running through our fabric and our templates to build the state we calculated for the entire network fabric. And then we push it out. Questions on this so far? If you guys have questions as we go through the entire training, by the way, please stop me and ask. I fully expect a number of concepts as we go through, especially in later days, will be things you guys haven't seen before. So please call it out and I'll address those questions.
Yeah, can you clarify that fabric logic portion of this?
Yeah.
So you had upstream data sources, so your inputs basically are those, then source of truth, but then fabric logic worked in there at that point. Not quite clear on that collection or connection.
Yeah, so effectively, one of the things we do a lot in our marketing and our position with customers is we have these verified designs we do. And our statement is always that these are based on patterns between the hyperscalers, they are repeatable, they are fast, they are better than your special Snowflake network you've had for the past 20 years. So the concept being, rather than someone trying to do like a collapsed star or a 3-tier topology that might have on Cisco, we tell them, nah, screw that. You've got spine layer, you've got leaf layer. And then you just algorithmically have this pool of addresses, you pick them out, you apply them. The concept being that by making these rigid rules, we make it easier for them to actually extend the network as they need to. So what you'll see in something like AVD is we have a number of basically fabric types they can pick from. So it's like, what do you want to deploy today? Is it an L2DC? Is it an L3DC? Is it a DC interconnect? And based on that, it asks you for some basic stuff like, what's your underlay peer-to-peer link subnet? You tell it that, and it calculates, okay, based on the subnet you've given me, I can have this many devices maximum. They're gonna have this IPs. Do I have too many devices? Things like that. So before we can get to the point where we're looking at calculating the actual final configs, we can start to make some intelligent design decisions about what we're going to be doing in terms of IP addressing, things like features, the data we're going to need about link connections, things of that sort. Is that make clear?
Yeah, that makes that clears that up.
Sure. And then I will put this in the sidebar as well in the chat here, just so you can see what I'm talking about. 1 second. I will give you the AVD docs to look at. We're getting started here. We'll go into this more on day 2 and day 3, but this gives you an example of what we're talking about when we talk about things like fabric logic. You'll see here in a design like this, what they're doing is they're doing things like designing device types, and they're also doing fabric-wide configuration parameters. So this is the kind of thing that really your network architect might be doing typically, where you're basically decreeing, we will follow this pattern, we are going to have these characteristics, and then your engineers sit down and they implement the architect's design.
I gotcha.
So, like we talked about, Ansible starts to merge some of this together for us. We can flatten the bunches together. We can make that pipeline repeatable. Ansible basically starts eating the back half of this pipeline here, so that then we can take this, we can drive it to devices. When we do this out CDP, Ansible ends up speaking to every device over EAPI directly. That may or may not be what you want in some cases. The way we usually position this with customers is that we inject CloudVision into the end of this here, like this. And in this case, CloudVision owns the API communication to the devices, which allows you to do things like drive changes to remote subnets with CVAS, which is usually where it comes in handy. There's also a project in place that is not done yet that is going to bring some of AVD and Ansible execution directly into the CloudVision environment through Studios. So you may see that in future releases. So with that out of the way, let's talk just some background in terms of terminology and concepts. Then from there, we're going to go into our Jinja primer and do some lab work. A few basic terms you're going to hear a lot this week are APIs. There's multiple kinds. API just essentially means it's an application programming interface. It's a way to talk to the program that is convenient for coding and not as convenient for humans in its most reductive form. When we talk about REST APIs, those are usually HTTP APIs, and they're going to be using a very specific style of how they structure resources and endpoints to call. We also have JSON RPC APIs. So as you can see, that's composed from JSON and RPC. Basically, you fire a blob of JSON at an endpoint that has details like the method you want to call and the parameters to run it with, and it does that. The biggest example you'll have of that in our product line is the API itself. It is a JSON RPC API, meaning you fire a giant blob at it and it gives you a blob back. YAML and Jinja 2 will come to play when we're talking about Python and Ansible. YAML is a backronym. There's two different things it can expand to. Neither of them are particularly important. All you have to know is that YAML is the file type, and someone made up something that it stands for. Jinja 2, quite flexible. We can set more, but basically it is what allows you to more or less do Mad Libs with your code in Python. So, like we talked about, APIs, they are an interface, meaning functions and procedures that allow you to talk to a program and communicate with it easily. If a program does not expose an API for use, it doesn't mean it's impossible to talk to, but it does make it significantly more difficult because usually you do end up doing something that looks like you're mocking a user. You might have to drive a headless web browser. You might have to mock a SSH console connection, things of that sort. It's very ugly. Some of you, depending on how long you've been working this way, you might be familiar with on some older vendor systems, you had to basically use pexpect and pretend you had a session to switch, and you'd have to do things like read the prompt characters to figure out if you were in enable mode or not, and then make changes based on that. That's all very ugly. What APIs like eAPI on our boxes do is they give you a much cleaner way to talk to the system and do what you actually care about, without having to wrangle all that dirty communication details. When you're looking at these are some decent visualizations to see what's happening under the hood. Effectively, with any API, whether it's local or remote, you have a client and a server. You'll see this on switches when you have terminal acting as a client to the config agent server, for example. You'll see it across the network when you've got your system, whether that's your laptop, CloudVision, or Ansible, talking to terminal in the box. You always end up sending some sort of request to the API with or without payload, depending on what you're doing. The API endpoint will go to the server and do some action on their side, which is opaque to you, and give you a response back. Key concept, fairly straightforward, but sometimes there are intricacies on this, usually around things like timeouts, payload size, things of that sort. The main way you're going to see and get exposed APIs at first is with these REST APIs we've been talking about. Again, they happen over HTTP. REST is an architectural style that describes how you layer and design the API. Most systems that call themselves REST APIs follow it to a point, or not what we would call truly REST because it gets a little obnoxious. But it's helpful shorthand to know that when we talk about a REST API, there is going to be a set of HTTP verbs they're using. So get, put, delete, patch, and endpoints are calling to manipulate the state of a remote system. So we talked about those verbs. In REST, the verbs matter. A non-REST system might end up using only get or post, but a RESTful system is supposed to use all of the HTTP verbs to be as descriptive as possible in when it's calling the endpoints, and the verbs matter. In REST, you might have the same endpoint that does different things based on the verb you call it with. The other thing with REST is that you always put scoping rules in the URI. You'll notice when we get to things like JSON RPC APIs that we really don't hit a descriptive endpoint. We basically hit an endpoint that just says do something, and all of the actual data about what we're scoping it for and the actions to take occur in the payload. So The other thing that's important too with REST APIs is that they are stateless. The request and the response from any given API transaction is theoretically independent of each other. There are some things that carry some minimal state. For example, if you have an endpoint that requires you to be authenticated, you might talk to a login API first. Login API endpoint, it'll give you a token that you then pass in later requests, or it might give you a cookie. But by and large, you are not carrying an ongoing conversation over REST APIs. With systems like gRPC or JSON RPC, you can actually have an ongoing communication channel between client and server with state in the system. So we have here is a screenshot of the REST API Explorer in CVP. What you're going to notice here is that when we came out with this in 2018, we called it the REST API, but it actually wasn't very RESTy. We weren't even using this full set of verbs we're supposed to. We were only using get and post calls. So for example, you would do like this last green one here, and in the first part, a post call to delete devices, and that would delete the device. That's technically not REST compliant because a delete call should be delete. So what happened is when we updated that and tweaked it some in the 2020 releases, you'll notice here we've actually collapsed these to where it's the same endpoint for all three of these calls, but the verb changes. And based on what verb you have, different operations occur. Delete deletes, obviously. A get pulls all your devices, and a post will add devices. That's the key of REST. And this layout here is something that's called Swagger. It's now called OpenAPI v3. And it basically is a system that can read a spec of an API and give you pretty color coding like this. An important thing to note too is that for CloudVision, while we still do have REST APIs, by and large, the devs have given up on us. We are now going to gRPC bindings for resource APIs. We have HTTP equivalents, but they are not considered RESTful. So this is what it looks like when you're working with REST APIs. There's a number of tools we can get into that allow you to do this sort of thing easily if you don't like using curl. There's, for example, Insomnia and Postman. Both of those are systems that allow you to craft API calls for REST with a GUI-based system and observe the response. But using curl, it's simple as this here. We set up a HTTP request to our system. We have a header in place saying, I will accept JSON as response. We have a target of where we're sending it to, and then the method is a get. And then from that, we get back a blob of JSON. So for those of you who've not seen JSON before in the wild, what this is basically is a big old mess of a list of a dict. And inside, we have another set of key and values, which are string types mainly. We'll get into JSON a little more later, but this is a data format that's easy to read for humans, and it easily translates with libraries in most major coding languages into their underlying data structures. So it's good to work with. There's also tools like JQ on the command line, which can parse this and make it easier to read by pretty-printing it, making it colorful, things of that sort. Questions so far about REST APIs?
You said the REST APIs on CVP, they exist still, but they're by and large being supplanted by gRPC?
Yeah, that's correct. So it's
Okay.
not just gRPC. The technical term for them is resource APIs because we have gRPC bindings for them. We also have HTTP bindings. So it's one set of APIs, but they have multiple implementations. And the reason they picked that was multiple. One, it's easier for them to create that way because they can specify the resources and Golang that way and build the API surface. And then we can do code generation to build the APIs. But two, they can be more expressive in their equivalent REST calls for the same amount of request and responses. One of the things with REST that hits people is because of how it structured itself to be REST compliant in terms of verbs and actions, you end up doing a very large number of calls. When you're using systems like JSON RPC or gRPC and the like, you can do very terse RPC calls to have a lot of actions taken on the server side.
Gotcha. Okay.
So, like we talked about, there is a REST API Explorer in CloudVision. You will be using this for a lab today. So just keep in mind, if you haven't seen it before, that's where you go. This is an older screenshot. It's roughly the same. There's more options on developer tools. And what it's going to give you is this system like so, where you have all your available API subsystems broken out. Within each of them, you've got your color-coded bands of what they are in terms of verbs and endpoints. And when you open them up like so, they'll tell you what they're expecting to get from you in a request and what they'll give you in a response, as well as a handy button over here called Try It Out, which will actually help you craft the call in your browser and send it to see what real data would look like when it comes back to you. So let's talk about JSON some. You've seen a brief example of it so far in that REST API call response. Let's dig into what it does. JSON started as an object system for JavaScript. It got adopted for a lot of other languages because it's a very lightweight way to store and exchange data while making it still readable for humans. Unlike binary formats, you can very easily inspect JSON and see what it holds to do debugging, with a trade-off being that it is somewhat larger. JSON is never the most efficient way to transport data around, but it is the most convenient. And like I said, most languages have bindings to it. You have those in Golang, Rust, Python, JavaScript, obviously, a few other languages where you can basically just take in a JSON blob and it will be converted to a set of data structures in your language. The key things you have to know about JSON are really going to be in terms of how we do lists and dictionaries. So what we call a dictionary in Python is called an object in JSON JavaScript, but same kind of detail. You've got curly brackets, you have some set of keys, you have values after every key. So like this bottom example here, if I'm getting back 2 keys in my object, where first key is name1, value Jericho, key 2 is name2, value Trident, that's what it will look like. And then because we can nest these data structures, you can have things like lists of dicts, you can have dicts of dicts, so on and so forth. And because of that, you can have this very expressive object structure to hold basically anything you can think of. So this is what it looks like on our boxes. Something that's very, very nice with EOS, if you've never seen another vendor, is that you can run basically any command to just pipe JSON filter and get the JSON response in the CLI. This is incredibly handy because when you do the same API call through eAPI, you know what the response will look like. Like you can see here in this object breakout we've got, when you show version and get our JSON response, we get back a single top-level object. It's got a number of fields here. For example, my uptime key has a floating point value of my uptime. Things like model name and version have string values. I've also got integers from mtotal, and I've got booleans for the international version, basically indicating if it's under controls or not. This is very easy to feed to your programming language of choice and parse to then do further actions on. And that's what makes this so effective. So when we take that composition we have from JSON and we slap a remote procedure call system on top of that, what you end up with is JSON RPC. RPCs, like we talked about, are more expressive than REST at the cost of being more complex. JSON RPC sits at a pretty good point on the curve here, where basically you just pass JSON blobs back and forth. Unlike gRPC, you don't need to know the specs ahead of time in terms of your communication format, your schema. You just fire off JSON and the endpoint tells you, that worked, I'll take it, or not, effectively. You do have to know, though, from prior documentation, what the endpoint can take. There is not typically robust discovery mechanisms available with JSON RPC APIs. So we've been talking about eAPI for a while. On every Arista switch where you have eAPI running, we expose this browser page called the eAPI Explorer. And what this does is it gives you this very slick way to actually compose a request, see what it will look like, and get the response back. So like you can see here, I have a lab.dot, and I told it, do a show version. I've got a set of options here. I run through, I tell it, hey, give me a response in JSON. If there's an error, stop. Some other basic details, and I fire it off. If you click this request viewer tab, you actually see the blob it sends of JSON to the endpoint. And then when I fire that blob off, I get a blob back, and it has my details. You'll see here, I've got a top level object that I get back from the server. And within that, I've got 3 keys. It's telling me the version of JSON RPC it's using, which is 2.0 always. It has my ID for request. This is used to track you get multiple requests in play at the same time, which is possible, but not often done. And then I have this result key here. The result key itself holds then within it a list. And that list has this object per response. If you run 3 commands, you'll get 3 objects in the result list within the top level object. And that's a pretty good example of how nesting starts to flow together in these objects. You can see fairly deep nesting fairly quickly, depending on what you're looking at, which is where tools to manipulate and parse JSON schema come in handy. So this is another example you recall where I have deliberately caused it to fail because I have not put in the complete commands. When you use the API, unlike the CLI, it doesn't do command expansion. So show mana isn't valid. You can see here then that my object has changed. The response I've gotten, while it's large and I can show on the screen here, has this new error key at the top level. Within that, it has data where my first command ran fine, so I have an object. The second did not, so it has an errors key telling me what went wrong. So obviously we've got different keys in the second response than appear in the first. Things like that have to be thought about when designing your interactions with JSON RPC APIs. Like we talked about, the actual schema for request, fairly simple. You're always seeing the same endpoint on the switch with these JSON RPC APIs. You are not changing the verb like you would in REST APIs. You're not changing the endpoint. It always goes to the same place. The 2 things that can change, and really only one is that will ever change in most things you do, is the method. Here we're calling the method run commands, which tells what to do. And then within that params object, the list of commands we're sending is typically what you would manipulate. And that's how you are structuring your requests to the server through a JSON RPC API. Questions so far on JSON RPC?
One question, Nathan. So can we also write it to a file? Let's say this JSON format that we are retrieving data into. Can we also save it into a text file, or let's say if I want to retrieve some of its information, I can probably make use of the dictionary data structure to just store as a key value pair. But is there a way we can store it into a file so that we have this entire set of, let's say I want the show running configuration, so I have all that particular JSON format file in a text file?
Yeah, so good question. I'll answer both there because I think you actually asked a second question. I don't know if you realized or not. Both YAML and JSON serialize cleaning the files, meaning basically you can take what you have here, dump it in a file. It's a valid text file. And then in your programming language of choice, like Python, you can tell it simply load this file into JSON and it will parse it and make an object. So they're very clean to serialize. There's no crazy binary encoding you're doing. There's no compression, just text file. Now, the second part of this, which might be what you're asking, but it's a question I get asked by SEs, is they'll go, hey, great, I've been using the API. I pulled the running config off. It's JSON. I want to make that into a text file now so the customer can save it in case later they need to copy and paste that running config onto a switch for something like an RMA.
Mm-hmm.
Again, very simple. Two things you can do here. One, in the actual API format, you can tell it text instead of JSON. So going back over here, we have both options. You can get back a text blob if you want, just store that. Or
Okay.
two, what you would do is you'd have a little bit of iteration. You take the object you get back, you would loop over the output of the object the command you ran, and
Right.
you would just write out to a file with the strings. So two ways you could achieve that if you wanted to make a text file from JSON.
Okay. Sure. Thank you.
So like we showed before, this is what it looks like when you get responses back. The key part here that is fun to look at is you'll see in our request, we have 3 commands which will never have responses. There's nothing to tell user when you do enable. There's nothing to tell when you do configure. It changes the prompt, it doesn't actually output anything. So when you have commands like this that don't have output on their own, what you will see in a JSON RPC response is just an empty object at that position in the list. So my first 3 results, empty, empty, empty. And then you'll see for the 4th command, it ran fine. But because I didn't have that access VLAN, it creates it and it gives me a warning back in the key, which I could parse then and report to a user. And at the end of that course, because my last command is a show command, there is output and it gives me the document for that. So let's move on to talk about YAML sum. YAML, like we talked about already, it's a backronym. It doesn't really matter what it means. You just have to know what, oh, sorry, Alexa, you have a hand up? Is there a question?
Yeah, Nathan, sorry, quick question. So when CVP pushes config changes to the EOS device, it uses eAPI, right? Although it goes for the Unix socket. So is it correct that the CVP uses config sessions to push everything? I believe so. And in this case, do you by any chance know how is this done? So is it just pushing it the same way with the raw CLI command and then gets back this the session config session ID and then just comes back a bit later and confirms it?
Yeah, so let's talk about the case real quick. It is relevant. Some parts are CP specific. So what happens is when you push config to a switch, whether to validate it or to actually save it, what happens is the first thing CP does is invents an ID. And the details largely don't matter for this discussion. Let's just call it random. So it creates this random identifier. And so then what it does is over from there on the box, it will open up this communication and says, hey, give me a config session with a random ID, and it knows what it is. So that config session gets opened up. We do a rollback clean config. And then from there, we start applying our commands. Once that's done, we then go and we commit that with a timer. So again, config session, random ID, we know what it is. We then make sure that communication doesn't drop. If it doesn't drop, within X period of time, we go to the device and we say, commit that config session. And because we know what it is on our side, it's all good to go. The reason that it's basically a random ID is that it doesn't conflict. If we have multiple change controls in play for some reason, we can commit the one we need. If we have a validation occurring, we know it's tied to that validation, so on and so forth. That's why often, if you look at your show config sessions on a switch when you're using CP, you'll see a really, really long session name. That's usually something like config validate UUID with a UID value or something like that. That's basically what you're doing there. And then, like you mentioned, we now use advanced logging most of the time. All this eAPI communication is correct. We're using the old school login. When we're going over Terminator, that's actually gRPC. So it changes somewhat. We are passing JSON at the end to the config agent, but we're wrapping that within a gRPC wrapper. So we get into some fun scenarios there about what it looks like in the wire. Does that answer the question?
Yeah, thanks a lot.
Also,
All right.
just a small
Go ahead.
question. Like sometimes, customer says that the management access or the CLI access to the particular switch has been lost, or they don't have the access to it right now. But if that device is streaming onto the CVP, can we make use of this eAPI to just retrieve a few basic commands to look at a few outputs and confirm what's happening?
It depends on why they've lost access. There's a
Okay.
couple of scenarios that can happen there. Let's say they've done something stupid and they've put an access list on SSH that blocks everyone for some reason.
Right.
Well, eAPI is not SSH, so we can still use it. Making communications there as long as it's on. Let's say they've made the scenario worse. They have SSH blocked. They have eAPI blocked. Well, if they're using advanced login and we can still have the device stream to CVP and they don't have AAA issue, we can still push configs from CVP and override the blockage there.
Okay.
So yeah, there are a number of ways programmatically we can attack a system, even if SSH is down or inaccessible.
Got
It
it.
really depends on what the issue is.
Sure. Thank you.
Obviously, it's a network problem. It's just, if you have a network issue, all bets are off.
Right. Yeah. Oh, thank you.
Yep. So YAML. YAML was, let's call it co-developed alongside JSON in terms of program history lineage. It comes more from the Python side of house. It has a few syntactic differences to YAML, although any data structure you can express in JSON can be expressed in YAML basically, and vice versa. There's some extreme edge cases that can't be expressed, but they are few and far between. Most of the time we're working with YAML, it's going to be because of Ansible. And at the end of the day, what will happen is you will feed YAML to Ansible. Ansible will output JSON towards your devices. When we get into what this does, you get something like this. So every YAML file is going to start with 3 hyphens. It's not always strictly needed, but if you don't start with that, it's not technically a compliant YAML file. They're always supposed to have 3 hyphens to start. Indentation within a YAML file is 2 spaces, and you have these key value structures. Effectively, it's doing the same thing that JSON is. It's just using white space as the limiter and not brackets. So depending on your preferences, this can be harder to read or easier. What you're looking at here in this kind of setup is I've got some top-level keys in a dictionary this would parse to. And within each of these keys, I have a dictionary object as the value. And then for these objects, I've got my key values here. And for the trunk group's key, that has a list inside of it. This hyphen space syntax means it's a list. So this is a basic primer of how this is represented, like we just talked about. You've got key values, you have lists, you have dictionary maps. These get composited together, just like in JSON, to create your more complex data structures. We have a concept in YAML of strings, we have integers, we have booleans. All of these get used together and they can represent the same things you would in JSON. Every Ansible playbook you'll come across, and we'll get more into this later, is a YAML file. What will happen in each of these, as you read these, is you will have effectively these top-level dictionaries that have some details. And within each of them, we can pass it down to create this full complex object. We'll walk through more in day 2 about how to read these, but effectively here, I have a top-level dictionary with some keys that we'll use in Ansible to do things like describe itself in playbook output, telling us where it runs, if it's gathering facts. It has a list of collections we'll need in Ansible to make it work correctly. Then you'll see here we have a list of tasks, and each task list item is itself a dictionary with further details. So Ansible, when it runs, will read this whole YAML data structure. It will parse it into a complex object, and then it will use that object in program execution to drive the outputs. When we start comparing JSON, YAML, and XML, which we don't really use XML a lot, but if you've ever seen it before, you know how verbose it is. You can see how these three different data description languages have different densities, really. Obviously, YAML is smaller than XML, but it's also a little smaller than JSON when pre-printed. Any JSON object can technically be reduced to a single line if you care about the number of lines something is. That makes it very, very hard to read. So you'll usually see in everything except wire serialization is that JSON objects are pre-printed, where you're basically separating out the brackets and the delimiters to multiple lines to make it visually obvious what the layout of the object looks like. With that spoken about, we'll get into Jinja 2. Questions on YAML? Okay, sounds good. So Jinja 2, it's a honestly really great DSL, domain-specific language for Python. If you've ever played Mad Libs as a kid, this is basically it. What it allows you to do is to write long strings. You could write a paragraph, you could write a sentence, you could write a book, and you put placeholders in those strings, and you say, make the value of this placeholder a variable. It allows additionally as well for some control logic. And so what this lets you do is build very large, very complex text quickly. The main way we use this in our products is for config generation for EOS switches. It's simple to install. When you're using your lab environments today, we are using AVD. So you will already have a VS Code system set up with Jinja installed, as well as the Ansible libraries. But if you didn't, and you want to do it locally, just pip install it. When we get into Jinja, I'll provide links to the documentation, but the syntax is very, very simple for the most part. There's a few main constructs you want to know about. Anytime you have a piece of your text that has single brackets and then percent signs, that is a control expression. That's going to be doing something like if logic. It's going to be a loop. It's going to be an include block, something of that sort. Double curly brackets means you're going to substitute a variable into the output. And finally, if you have curly brackets with pound signs, those are comments. Those are things you're putting into the template just for your own awareness of what it's doing. They do not get emitted in the output of the template. The fun thing you can do too with all of this is there's a concept of filters in substitution for Jinja. So it's not just that you have a variable that you load into a template and it outputs. You can feed them through Python functions to transform them before emitting them. We have used this in a bunch of really fun ways in AVD in some cases. For example, we have a Jinja template, which I'll show you on day 3 or 4, that takes an IP subnet pool, runs it through a Jinja filter to calculate the correct point-to-point address for a given interface, and then emits that value. So we can do things like subnet math directly within our templates, thanks to Jinja. So looking at Python here, it's very, very simply as Jinja. In this example, what we're doing here is we are defining just a simple setup where I've got my values for my template. I have an inline string defined as my template. So what you're seeing here is I have a control stanza checking to see if these variables exist, and they're not none. And then within that, if these are met, we output this line and substitute in this value. When I build a template object from this string, and then I call render on that object, you get out this output, clean and simple. In most cases, you won't define your templates inline. You will load them from a template file. You'll see some examples of that today. We'll get into this more during our lab section of the class.
A quick question about that template load.
Sure.
I know for the render, if something goes wrong, Python is just going to throw an error. Is there any linting or error catching on the template load itself to verify that this is valid Jinja? Or is it just say, I'll trust you?
Yeah, so the object internally has a number of structures that will be validated. And if it can't create the object, it will throw an error. And if you don't catch it, of course, program explodes. If you catch it,
Awesome.
you
Okay.
can use trace and everything else. Yeah, but like if you have an unterminated expression in the template, for example, the template creation call will fail. You are
Got it.
evaluating the template. Yes.
Okay, that's good. Excellent. That was my main question there. Thank you.
So if statements, these are going to be everywhere in AVD. We use them heavily for feature level support. Ansible as well to some extent, but we take it up an extra notch. Effectively, with if statements in Jinja, you can test if a condition holds true and then output something or not output something based on that. So for example, when you're looking at things like AAA configurations in our generated code, what we're doing here in this example, if you look at the second line in green there, we're checking to see if the user has specified a variable about AAA authorization. If it exists, then we'll go ahead and we'll emit a AAA config. If they didn't define a variable about it, we just skip it. And you'll see here as well, we're also showing off how we use nested ifs. So in this setup here, if you don't match this stanza, we drop through and we run this branch of the template. So we can actually have branching conditionals at the template level, not within our Python code itself. So we can put all our business logic in the same place for doing config generation. And all Python ends up doing is just loading your variables and slamming them into the template. When you get to using these for Ansible, it looks more like this. A couple of files from the screen we'll walk through. My AAA.j2 is my template file. By convention, J2 is your extension for Jinja templates. Most major IDEs will recognize that and then color code your templates accordingly. They will flag in colors for you what your various standards are doing. They can even lint your templates for you. Both VS Code and PyCharm have linters in the IDE where they can warn you about problems before you can run a template. Like you're seeing here, I've got a comment on the top line just saying, hey, this is a template for doing AAA authorization EOS. I've got my if stanzas, my outputs, and all that. We take that, we take group bars from Ansible, which we'll get into later, which has our actual spec here about what we're doing in terms of variable creation and the value of it. We take this through, we run our tiny playbook that just outputs the result of this template to a file. And when you add all these together, you get this configuration. This is the heart of what we're doing with Ansible a lot. We take variables, we make text, we put text on a box. It's that simple. We just start layering on complexity. We get into things like conditional includes, for loops, subnet math logic, things of that sort. But at the heart of it, we are taking data we have, we are transforming it, we are loading it into switches. And doing that at scale in a repeatable manner is what makes us so powerful and effective for networking. Now, same thing in Python. If you don't want to use Ansible, again, very simple. All you'd be doing here is you just load in the template file with your context handler as usual, and then you build the template from the file, a 7-line string. Same concept as earlier, results the same. So let's talk about loop sum. Loops are another fundamental construct in Jinja. They operate the same way your for eaches will in Python. Effectively, what we do when we're running a loop is we go in, we say for item in list, do something. So here, like you can see with this, first we're checking to see if VRFs are defined. If we don't have any VRFs, we don't even need to run this. If we do have VRFs in our config that we're injecting into the template, for each of them, we go through and we emit this line. like we talked about as well, filters exist within Jinja. They can do a lot of things, and you can make your own. I have a list here in the slides of what the built-in filters are. I believe last check there's about 20 of these, and then you can make your own and add them to a Jinja object within Python. So we use these for things like subnet math, we use these for validation, different operations that sort. When you call a filter, it's always in this syntax you see here in red. You have your substitution, like you would usually for a variable, then it is piped to a filter. And Jinja interprets that and runs that. It will take this variable, it will run it through a Python function called upper here, that's registered to that handler, and it will take the result of that and load that into the template at this point for your output. And again, simple examples running through. We've got a loop here. We've got filters. Given this input dictionary, when you run this through a playbook, you get something like this. What we've done is for each interface we had in this input dictionary, we went through and we output a description, but we took the string and we converted it to uppercase because the filter here, which then gives you this consistency in the final output. You always know your descriptions are uppercase, regardless of how they were entered. Questions so far on Jinja? I'm assuming this is probably new to most of you. It will make sense more once we get into the Jinja lab, I promise. But the best way to work with this is by trying it out. Okay. Final topic of the day. We are going to give you a blitzing primer on Git, just so you can use it for some basic storage in your lab. I am not going to cover all the ways Git can be used here because it gets very complex very fast. We're going to talk about simple operations today. The reason Git is important, especially when talking about network automation, is because it allows us to do version control. We can have multiple sets of the same code base that's describing network fabric throughout time with different feature sets and different intents. So there's a lot of ways this can be used. You could, for example, realize you made a bad change at some point, roll back to an older commit and redeploy that to fix a mistake you made to the network. You could be making changes in a branch alongside your main network logic, test out a new feature, things like that. There's a lot of ways it can be used. We're going to just cover the very basics of that so you can store your lab work and come back to it later and get some familiarity with the actual commands. When we talk about Git, there's a couple concepts come into play. Your files and your directories live in what Git would call the workspace, and that's just your file system. When you go to store the current iteration of those files into Git, they're first added to the index. Index is a staging ground that we're using to store changes to files before committing them. There is nuance to that. You don't have to always commit all the file. You don't have to commit all of the files in the directory either. But effectively, you're taking some set of changes to files, you're putting them in the index. Once the index is in a good state with the changes you want, you go ahead and you commit those. At that point, Git creates a commit in its tracking system, and it has contents of files, and it will also describe how to get to that content state. I'm extracting some details here, so for those of you who used Git before, there are some things we are not going to cover with that, but this is a general operation of how Git works. There is, of course, like you're seeing here in the slide as well, porcelain around the commit commands. If you decide that you don't like working with a staging index, you can bypass it basically and just take all your changes from your workspace and load them into your repository with git commit A, which takes all the changes from all your files and loads into a single commit and stores that. And at that point, you now have a commit in your repository. You're not going to have just one commit. As the project lives over time, you keep adding more commits to it, what's called a commit tree. And when you're looking at the history of the project for troubleshooting, bisecting, pulling all changes out, what have you. You're navigating a commit tree. You'll also end up pushing changes from your local Git repository to a remote repository typically. Git is distributed, and most of the time when teams are working with Git, they will have a centralized Git server on something like GitLab or GitHub. They will make changes to their local repository, and then they'll push them up to the remote repository where changes from various people and their branches are synced and stored. As people make changes, you'll pull down the contents of that remote repository to your local system. And that's how you actually update your working files on your file system to get their changes in front of you to work with. For most of what we're doing in this course, the things you're going to care about are going to be the git add commands, the git commit commands, and optionally checkout or unstage. I've got slides in here that walk you through most of how these changes work. The main thing you want to know as well for Git for these labs is that we include answer keys for every single lab, but they're implemented as Git branches. So if you need to see the answers for a lab, you have to use Git. Effectively, what will happen for that is you'll be using Git checkout with a branch name, and it'll show you the answer keys. Again, we can cover that more in the lab section once we start working in the labs, but it helps you be aware that that's how we do parts of this course material. So, like this is showing here, for a given set of changes to files in your working directory, when you stage them, they go to the index. Index changes get wrapped into a commit, put into the repository. If you add a change from your working directory, the index that you later decide is not ready to be committed, you can back it out. When you back it out, you will not be committing that as part of the commit. You can add it later. It just will be part of that batch of operations. So when you're using Git, a few commands that will be important we're going to run through as far as CLI examples. We're assuming for these examples that you have already set up your directory as a Git repo with the git init command. What this here is showing you is the output of Git status when we have just set up a Git repo on the CLI, but we have not made any commits yet. So you can see we're on the main branch. There's been no commits, and Git is aware that we've got these files in our directory and it is not tracking currently. Okay, so how do we use this? At this point, we have these files with changes that we aren't tracking in Git in the working directory. They're not in the index, they're not in the repository. From here, we want to put these files in the directory in the index and eventually the repository. We're going to do this with the git add commands. When you git add a file, again, it puts that in the index. Like you can see here below in green, we're now saying we have these changes staged for commit in the index. They're not yet committed. So here, we're going to add the changes we found for leaf 2 to a commit. If we were to commit right now, we do not yet have commits in the index, changes in the index for leaf JSON or main.py. So we run through, we add the other files with just git add dot, so glob expansion, all files in directory. We can now see that we will, at this point, if we do a git commit, add changes from all three of those files into this commit. So going back to our visuals, all three files have their change in the index. They are not yet in the repository. At this point, if we decide that the leaf.j2 file, our Jinja template, is not ready to be committed, we can do a reset. That backs the changes to that file out of the index. They still exist in our workspace. So at this point, you have that file back in the working directory as far as changes. Your change to two other files are in the index. Again, nothing is committed yet. At this point, we want to move things from the index to repository. We go through, we do git commit. This M flag here you're seeing is the message for commit. If you don't use that, you have to enter a commit message when it opens up an editor in front of you, and it stores that and creates the commit. At this point, then you'll see it runs through, tells you, okay, these files changed. We had this many new lines added, this many lines removed, if any are removed. And then once you do get status, you'll see that now the index is clean, working tree is clean, there's no changes to commit. Terrific. So we have our changes persisted in the repository. At this point, then, we can go on and make new changes. In this example here, we go through, we add an extra VLAN to our leaf JSON file. Git picks up the change that's happened there. It tells you, hey, this file's modified. At this point, we have options. Because we now have a commit in Git, if that was a bad change we didn't mean to make, and we can't undo it with our IDE or our editor because it was too long ago, we can pull the old version of the file out of Git and restore it. Git restore leaf.json will bring the previous version of that file out of the Git repo and load it into your working directory. Very helpful with the undo feature. If we're intending it and when we run it forward, we would do git add and git commit them to record that change into repository. So this is the heart of what it means when we talk about version control, is that we can have these various versions of files with the changes we made. We can look how they change over time. We can pull out old versions if needed. Again, very powerful talk about config deployments and changes to our network. If we do something like this, where we're like, oh, we changed what VLANs go where and that was bad, we can check out the previous Git version of our files, run the playbook again, restores the network state. Very handy stuff. And of course, we have diff features, which are always handy. Like you'll see here, a little hard just because we've got different shades of green. Our olive color is our main output. Things in red have been removed. Things in bright green have been added. So you'll see in a git diff, if you have a change of a line, you'll have a line removal and a line add. So effectively, it's telling you is that for this line, that's the old one, this is the new one. Very handy looking through changes. Let's say a customer opens a case, they say, hey, something changed in AVD, and now I can't deploy. Okay, are you using Git? Terrific. Let's look at a diff. When did you change it? Okay. This is the entire delta of your configs. It's probably this issue is in here somewhere. So, same concept. When we're adding files, if they're in the index, you won't see a diff there because by default, the diff command is comparing the change in the working directory to the repo. If you need to diff a file that's had the change pushed to the index, you need to add the index flag. Or sorry, cached. I'm going to skip part of the example here because we're just going more into how we would use the diff. Like we talked about previously, the other thing that Git allows us to do is that it is not a straight line of config versions. We can branch these and do feature testing or changes off the main branch and then merge them back to main if we decide they're worth it or leave them for other reasons. This is part of how we do deployments here. When we cut a release version for EOS or CVP, what we're doing basically is we're starting up a branch at that point in the main tree, and that is your release target. As we release maintenance upgrades to that train, we are cherry picking commits from the main branch onto that release branch. By keeping it separate, we can be reasonably sure that change to mainline will not introduce new bugs to that branch because we're cherry picking explicit commits to bring in as fixes. So with this, we're going to get into lab time. Lab time today is a little extended from other days because we want to make sure you guys have time to work through these, get set up, and get familiar. We are going to have 4 labs to do today. All of you at this point should have your lab access token I gave you. If you did not get one from me, let me know. What you're going to do is you are going to click the link to bring up your lab page. You'll hit start. Within 10 minutes, it should be online. We are using a new topology from last year because ATD has deprecated the old single DC model. So we're using what's called the dual DC topology. This is going to give you a lot of switches to work with. You want to make sure you can get into these topologies in question. I'll put this link in chat as well. This has the labs for today. And when you look at this, what you're going to see is that we have days 1 through 3. Day 4 is continuation of day 3. Day 1 has all of your labs for today. And when you look at your branches, we have answer keys as well. I've run through all your labs for today. They should all work with the dual DC design. If you hit an issue, please let me know. We'll be on this still. We'll be open question at time. You need any questions answered. What you'll do once you have your topology up is you will actually clone this repository into your VS Code instance inside of ATD. And to recap, as far as topology, this is what you're working with. Obviously, you can see there's some scale to it. So this would be the sort of thing where it starts getting a little unwieldy to do by hand in a reasonable amount of time. But with automation, it speeds up dramatically. When we're talking about what labs you're doing today, hang on here, there we go. There's going to be 4 different things you're doing. First lab is going to be just getting your feet wet with basic use of JSON RPC APIs with EOS and raw Python. So what you're going to be doing is using the request library in Python to craft a JSON RPC blob to fire devices, get a response back, and print it out. For each of these labs, the lab repo has a more detailed description of what you're going to be doing, as well as an example of the output we expect. Lab 2 is going to walk you through using Jinja to format the output from lab 1. So using that code, you'll run through, you'll take outputs, you'll print nicely with Jinja. Lab 3 will be getting into using Cloud Vision REST APIs. You're going to have to find the endpoint in question to use, and then write a Python script to talk to Cloud Vision, get some output, and print it. Lab 4 is fairly simple. You're going to be setting up a GitHub account or repository, you don't already have one, and then pushing your files there. So to recap, we're going to be doing some API work, we're doing some Jinja work, we're talking to the REST API, and then you're doing a little bit of Git pushing. Questions on this overall?
You said you're going to post the link to that repo in the Zoom
Yep,
chat.
1 second here. So yeah, what will happen here is I'm going to post that, and then I'll be on for the rest of our time here. Any questions you have, I will answer. Feel free to work together as well if you need to on these labs. The labs are timed to where they should be completable in the sessions every day, but I know that's not always the case if things arise. So if not, you can always ping me for help as well. But I do recommend doing all the labs because they build on each other, and you skip one, layered content might be a little harder to pick up.
Hey Nathan, just had one more request. I think a lot of us are from the Vancouver tag team. So and on Friday we have a stat holiday.